Welcome back. Let's look at the remaining sections of Chapter 6, Manipulating Polynomials. Our upcoming roadmap includes special products, factoring quadratics, and advanced polynomial manipulations. In today's intensive session, we are going to fully cover 5 main sections. We will completely master from section 6.4 all the way to section 6.8 in this class. Get ready to dominate special products and factoring polynomial quadratics. Let's explore the geometric meaning of special binomial products. Consider a large square with a total side length of a plus b. We can divide this large square into 4 smaller regions. One square with area a squared, another square with area b squared, and 2 identical rectangles, each with an area of AB. This visually explains the expansion formula. Now let's remember these 3 special binomial products. Given any real numbers a and b, we have 3 core identities. First, the square of a plus b equals a squared plus 2ab plus b squared. Second, the square of a minus b equals a squared minus 2ab plus b squared. And third, a plus b times a minus b perfectly results in a squared minus b squared. When you expand the quantity of a plus b squared, you always get an ab term. Let's check this mathematically using the distributive property. The square of a plus b can be written as a plus b times a plus b. Distributing the terms, we get a squared plus ab plus ba plus b squared. Since ab and ba are identical commutative terms, we combine them into 2ab. This beautifully results in a squared plus 2ab plus b squared. Let's solve a perfect square binomial expansion problem using an area model. Our new example asks us to expand and simplify the quantity 3x plus 2 squared. Geometrically, this is identical to finding the total area of a large square with side length 3x plus 2. Let's visualize this area model on the screen. Step 1. Let's expand this mathematically by putting the expression in the form a plus b times a plus b. The quantity 3x plus 2 squared is equal to 3x plus 2 times 3x plus 2. Now, we expand the parentheses using the distributive property. 3x times 3x is 9x squared, and 3x times 2 is 6x. Then, 2 times 3x is another 6x, and 2 times 2 is 4. Step 2. Finally, let's combine the middle-like terms. Notice that we have 2 identical 6x terms in the middle, just like the 2 rectangles in our area model. Adding 6x and 6x beautifully gives us 12x. Therefore, our fully simplified final trinomial answer is 9x squared plus 12x plus 4. The perfect square binomial problem is completely solved. Let's explore another special product. When you expand a minus b squared, the middle term is always negative. Our new example asks us to expand the quantity 2x minus 3 squared. Geometrically, we find the area of a smaller square inside a large square with side length 2x. Let's visualize this subtraction area model on the screen. Step 1. Let's expand this mathematically using the distributive property. The quantity 2x minus 3 squared can be written as 2x minus 3 times 2x minus 3. Distributing the terms, 2x times 2x gives 4x squared, and 2x times minus 3 is minus 6x. Next, minus 3 times 2x is another minus 6x, and minus 3 times minus 3 beautifully results in positive 9. Step 2. Finally, let's combine the middle-like terms. Notice that we have two identical negative 6x terms in the middle. Combining minus 6x and minus 6x gives minus 12x. Therefore, our fully simplified final trinomial answer is 4x squared minus 12x plus 9. The calculation perfectly matches our geometric model. Let's solve example 2, focusing on the perfect square trinomial with subtraction. Our new problem asks us to expand and simplify the quantity 4y minus 3 squared. In the diagram, 4y minus 3 squared is exactly the same as the area of the darker inner square. Let's visualize this geometric relationship on the screen. Step 1. Put the expression in the form of minus b times a minus b. The quantity 4y minus 3 squared is equal to 4y minus 3 times 4y minus 3. Let's expand the terms step by step. For y times 4y gives 16y squared. For y times minus 3 is minus 12y. Then, minus 3 times 4y is another minus 12y, and minus 3 times minus 3 is positive 9. Step 2. Finally, let's combine the middle-like terms together. Minus 12y beautifully simplifies to minus 24y. Therefore, our fully simplified final trinomial answer is 16y squared minus 24y plus 9. The calculation perfectly matches our geometric model, and the solution is complete. Let's explore how the greatest common factor, or GCF, serves as a divisor. The greatest common factor of a set of monomials is the largest possible divisor of all monomials in that set. To find it, a great strategy is to break down each expression into its smallest prime components and then gather the matching parts shared by all of them. Let's practice example 1 with our brand new set of expressions. Find the greatest common factor of 12 a cubed b squared, 16 a squared b cubed, and 24 a to the 4th b squared. Start by writing down each monomial as a product of the smallest factors possible, expanding the coefficients into prime numbers, and writing out each variable. Now let's list all the numbers and variables that are shared factors of all three terms. They all share two 2's, two a's, and two b's. These are called the common factors. By multiplying these shared pieces together, 2 times 2 times a squared times b squared, we beautifully find our final greatest common factor answer for a squared b squared. Is there a faster way to find the GCF without expanding everything? Yes. You can also find the GCF of two or more monomials by simply multiplying together the GCFs of each of the different parts. Let's apply this shorter method to our same example expressions: 12 a cubed b squared, 16 a squared b cubed, and 24a to the 4th b squared. Let's break down the problem into different parts. First, the greatest common factor of the coefficients 12, 16, and 24 is 4. Second, consider the variable a, the GCF of a cubed, a squared, and a to the 4th is a squared. Finally, look at the variable b. The GCF of b squared and b cubed is b squared. Now, we simply multiply all of these individual GCF parts together. So, the greatest common factor of 12 a cubed b squared, 16a squared b cubed, and 24a to the fourth b squared is 4 times a squared times b squared. This instantly gives us 4a squared b squared. As you can see, both methods yield the exact same answer, but this way is much faster. Polynomials can sometimes be factored too. When a polynomial can be expressed as the product of two or more numbers, monomials or polynomials, those smaller components are called factors of that polynomial. To find the factors, the best first step is to identify the greatest common factor of all the terms. Let's check out our new example expression, 8n to the fourth minus 6n squared. Step 1. Let's find the greatest common factor of our two terms. For 8n to the fourth, the components are 2 times 4 and n squared times n squared. For minus 6n squared, it's minus 2 times 3 times n squared. The shared factor present in both terms is 2 and n squared, so our GCF is 2n squared. Next, rewrite the expression with this factor taken out. This beautifully leaves us with 2n squared times the quantity 4n squared minus 3. Step 2. It's always worth checking your factoring by multiplying out again. Let's distribute 2n squared back into the parentheses using the distributive property. 2n squared times 4n squared is 8n to the fourth. And 2n squared times minus 3 is minus 6n squared. This perfectly returns us to our original expression, proving that our factored answer is 100% correct. Let's look at an alternative method for taking out factors. We will factor the expression 9x cubed minus 6x squared. First, let's find the greatest common factor of the coefficients and the variables. Now, to rewrite the expression, we multiply and divide the whole terms by our greatest common factor, 3x squared. By doing this, we successfully factor out 3x squared, leaving 3x minus 2 inside. This is our final factored expression. We can take out polynomial factors too. Let's look at this expression. Open parenthesis, y plus 3, close parenthesis, times x squared, plus y plus 3 times x, plus y plus 3. Notice that each term contains the exact same polynomial block, y plus 3, as a common factor. To factor this out, we place y plus 3 outside the parentheses, and then divide each original term by y plus 3. This perfectly leaves x squared plus x plus 1 inside the block. We have successfully grouped the entire polynomial factor. Let's learn how to factor a quadratic polynomial. We want to factor the expression x squared plus 7x plus 12. To factor this, we need to find two numbers that multiply together to give 12, and at the same time, add together to give 7. Using these two numbers, 3 and 4, we can write the factored expression as open parenthesis x plus 3 close parenthesis times open parenthesis x plus 4 close parenthesis. To be absolutely sure, if we expand out these parentheses using the distributive property, we get x squared plus 4x plus 3x plus 12, which simplifies back to our original expression. The factors are perfect. If you see a common factor in each term, such as a number or a variable, you must always take it out first. Let's factor this expression, 2x squared plus 14x plus 24. Notice that every single coefficient is divisible by 2. So let's factor out 2 first. Great. Now, the quadratic expression inside the parentheses, x squared plus 7x plus 12, can be factored even further using our previous method. Since 3 and 4 add up to 7 and multiply to 12, it breaks down into x plus 3 times x plus 4. Therefore, our final, completely factored expression is 2 times x plus 3 times x plus 4. When you cannot find a common factor, you need to factor x squared plus bx plus c by trial and error. Let's look at this expression, 2x squared plus 7x plus 3. We must find factors of the leading coefficient 2 and factors of the constant term 3, such that their cross products add up to the middle term, 7. Let's test the combination. We arrange 1x and 2x on the left, and 3 and 1 on the right. Multiplying crosswise, 1x times 1 is 1x, and 2x times 3 is 6x. Adding 6x and 1x gives exactly 7x, which matches the middle term. Therefore, our final factored expression is open parenthesis x plus 3, close parenthesis, times open parenthesis, 2x plus 1, close parenthesis. Let's solve another advanced example. We want to factor 2x squared plus 9x plus 4. First, let's write down the possible factor pairs. For the leading coefficient 2, the pair is 1 and 2. For the constant 4, the pairs could be 1 and 4 or 2 and 2. Let's test which combination gives 9x. The combination that gives exactly 9x is open parenthesis 2x plus 1 close parenthesis times open parenthesis x plus 4 close parenthesis. Let's double check this result by expanding it out. Multiplying the terms gives 2x squared plus 8x plus 1x plus 4, which perfectly matches our original equation. Therefore, our factorization is completely correct. Looking carefully at the signs in the quadratic can help you work much faster. Let's factor this expression, 2x squared plus 11x plus 5. Here, the constant c equals 5, which is positive. This tells us its factors must have the same sign, either both positive or both negative. Now look at the middle coefficient, b equals 11, which is also positive. Because the sum must be positive, the factors cannot be negative. They must be positive. This eliminates the negative options instantly, narrowing our choice to +1 and +5. Therefore, we immediately get the correct combination, 2x plus 1 times x plus 5. Quadratics with two variables can also be factored using the exact same method. Let's factor the following expression x squared plus 6xy plus 5y squared. To fill the gaps, we need two terms that will multiply together to make 5y squared, and at the same time, add together to make 6y. Let's test the expressions that multiply to 5y squared. 5y squared and 1 add up to 5y squared plus 1, which is incorrect. However, 5y and y add together to make exactly 6y. This matches the middle term. So, our final factored expression is open parenthesis x plus 5, y close parenthesis times open parenthesis x plus y close parenthesis. Trial and error can be tricky if there are more possibilities. Let's factor the following complex expression, 3x squared minus 10xy plus 3y squared. First, 3x squared can be factored into 3x and x. To fill the gaps, we need two negative terms in y that multiply to positive 3y squared and cross-multiply to give negative 10xy. Let's try out some sets of parentheses. First, trying 3x minus 3y times x minus y gives cross terms of negative 3xy and negative 3xy, which add up to negative 6xy. This is incorrect. Second, trying 3x minus y times x minus 3y gives cross terms of negative 9xy and negative xy, which add up to exactly negative 10xy. This matches perfectly. So, our final correct factored expression is 3x minus y times x minus 3y. Let's factor the expression x squared minus 49. First, substitute x squared for m squared and 49 for c squared. Since the square root of 49 is 7, we can rewrite it as x squared minus 7 squared. Applying the template, we get x plus 7 times x minus 7. Always watch out for the opposite signs inside the parentheses. The square of a binomial results in a perfect square trinomial. The pattern states that open parenthesis m plus c, close parenthesis squared equals m squared, plus 2mc, plus c squared. Let's see how this structure behaves. Let's factor the perfect square trinomial x squared plus 6x plus 9. First, substitute x squared for m squared and 9 for c squared. The square root of 9 is 3, which perfectly matches our middle term since 2 times 3 equals 6. Applying the equation backwards, we immediately get open parenthesis x plus 3, close parenthesis squared. Sometimes you need to group terms together before you can see any common factors. Let's factor this expression by grouping. For x, plus 7sx minus 8m minus 14sm. First, let's group the first two terms and the last two terms together in parentheses. Next, factor out the common factors from each group. The first group has a common factor of x, leaving 4 plus 7s. The second group has a common factor of negative 2m, also leaving 4 plus 7s. Now you can see another shared common factor block for plus 7s. Using the distributive property, we factor it out to get our final result, x minus 2m times 4 plus 7s.